Okay, then let's start with today's talk. So we are happy to have Maria Ubiali here to tell us about the interplay of global PDF and SMEFT fits. Please.
Okay, thank you very much. Thank you, Sven, and everybody for the invitation and for organizing this nice workshop. So in today's talk, I'd like to talk about something I've been thinking about in the past couple of years, which is this really interplay between the PDF fits and the SMEFT fits. So I would like to tell you a bit about it, and please feel free to interrupt me at any point so that we don't have to wait until the end to have a discussion. If there is anything which is unclear or anything that I forgot to mention, please just stop me. So, you know, the point is that we have seen in this workshop that thanks to these extremely precise LHC data, as well as advances in statistical techniques and theoretical predictions, of course, this allows us to extract the standard model parameters as well as some beyond the standard model parameters from the data to a great level of precision. We have seen the Atlas measurement of alpha S, the mass of the W. We keep having updated Parton distribution function sets and fits of the Wilson coefficients in the SMEFT and so on and so forth. I could go on forever. And what I started to think is that, you know, while there has been really a huge progress in determining each of these key ingredients of theoretical predictions, I think it's not yet evident how to combine all these partial fits into a global interpretation of the LHC data. And I think that simultaneous fits are really important in this direction. So I will especially talk about PDF and SMEFT fits, but this is true for also if you even want to stay in the standard model realm, as I will mention towards the end. So I will try to make a case to say why it is a time to start studying the interplay between the PDFs and possible new physics contamination. And then I will tell you a bit the steps that we have done in the recent year. So starting from a tool to perform this kind of fits, and then two examples, one in the sector of Drelian and one in the top sector, and then a recent study that came out just before the summer about really that answers better the question, can PDF absorb new physics? So let me start with the introduction. As you all know, all the theoretical predictions that we do at the LHC, most of them rely on collinear factorization, in which we separate the long distance universal information on the proton structure from the short distance Parton interaction hard scattering. So we know that we can schematically write a proton-proton cross-section that goes into AB like the Parton luminosities, which is the Parton distribution function, times the Parton cross-section for Parton ij going to any final state AB, okay? Plus corrections, which we know are important, but okay, at the moment I will not talk about it. And how do we determine the Parton distribution functions? We know that the dependence on mu is something which is predicted via perturbative QCD thanks to the Diglap evolution equation that now are known to really high precision, nearly NQ below. But the X dependence on the Parton distribution function that parameterizes the proton in terms of its Parton is something that we need to extract from the data. So once we have a parameterization of the PDF, which is determined from the data at a given scale, then we use them as an input at any given scale, okay? So this is really thanks to the power of perturbative QCD and universality of the PDFs. Very good. So how do we, oh no, that's a thing that happens. Okay, so that's a problem. Okay, so this slide disappeared. I didn't check the PDF, okay. Okay, let me just try to remember what was written in this slide. I think it's a compatibility between, so on my laptop they were fine, but I think on this laptop they disappeared. It doesn't matter. Okay, so let's try to imagine what is written here. So these are the theoretical predictions for, you know, let's imagine you want to extract some parameters from a fit. So what do? You minimize the chi-square. So the log likelihood to the data and the chi-square. So let me write it here. So you have a sum over I and J of this is the theoretical prediction for the point I minus the data I, and then you have the covariance matrix that includes all the experimental uncertainty and correlations, ij to the -1, and then you have tj minus dj. Okay, so this is the quantity that we minimize in order to determine the parameters. And here I split the parameters that the theoretical predictions depends on in two sets of parameters. Theta are the parameters of the PDF, and C are any other standard model or beyond the standard model parameters that we use, okay? So what we normally do, so if you do a PDF fit, so that in the theoretical prediction, you vary theta and you set all the other coefficients to some fixed value, okay? So it could be alpha S, the mass of the W, the whatever, so the CKM parameters. But in particular here, I'm talking about the C as the Wilson coefficient that you can add onto the expansion of your standard model to parameterize in a less model dependent way new physics corrections. Okay, so in particular, if we talk about this SMEFT, C is equal to 0. So you set all the Wilson coefficients to be 0. So you do a fit purely in the standard model, okay? If you instead do a SMEFT fit, what you do, you have the theoretical prediction and you set the PDFs to some theta bar. So you fix a set of PDFs which have been determined implicitly assuming that C is equal to 0 and assuming other parameters, and you vary the Wilson coefficients, okay? So these are the two things. So in a sense, they are orthogonal, so we got, and it was a very nice illustration which disappeared, but okay. So this is not a, yeah, sorry, go ahead. Yeah. I will get there. So I think in the study that we are doing simultaneously, we get up to 25 Wilson coefficients at the same time as the PDF. Yes.
Can you get any bias? I mean, that you first fix the standard model to get the theta, and then you use the theta fix frequency. So could it be that you overlook something is theta?
Yeah, exactly. So this is the question which I have in my research program. So are we putting some kind of bias, or are we ignoring some kind of interplay between these things? So what you ask is exactly the question that I'm trying to answer in the next slide. Okay, I will upload the right slides afterwards. Sorry about that, you know, I didn't check it here. Yes. That's it. Yes, exactly. Oops. It depends on different fits. So it goes from, if you have a fixed polynomial parameterization, you start from maybe 20 parameters for 7 independent PDFs, or you can go, for example, in the NMPDF, you have a very large parameterization, like 300 parameters, but where many of them are redundant. Okay, so or you have bases of polynomials. So anyway, from 20 to 300, let's say, it's a wide range. Okay, cool. Thank you. Okay, so, and the other thing I wanted to notice, so this is the typical kinematic plane where you put all the data sets that are included in a PDF fit, okay? So it's good that we include lots of different observers from deep inelastic scattering, fixed target Rayleigh, and LHC data. So the point I want to make here is that we include more and more high energy data in our fit in order to determine the proton, especially in the large X region. Okay, so if you look at the scale, many of the data are in the TeV region. Okay, so they come from the jets, from the top, from the high mass Drellian. And the same data that are used here are used in the SMEFT analysis, okay? So maybe binned in different distribution, but it's really the same information, the same experimental information that is used in both words. And the overlap between the data that are used in the PDF fits, because we want to know the large X partons, and the data that are gonna be used in the SMEFT fit, because we want to know the correction to the high energy tails that we get from higher dimensional operators, is going to be enhanced if you go in the high luminosity LHC phase, okay? So that's the point. We want to have more luminosity to get more statistics in the poorly known high mass regions, okay? Very good. So in principle, when I started to have this question, some people say, but okay, PDFs are low scale quantities and new physics is a high scale quantity. So why do you care about the interplay? But somehow, and in principle, what people do, which is, doing a PDF fit without considering any potential high-scale contamination due to new physics, or doing a SMEFT fit by assuming that the PDFs are standard model makes sense. But I think that the complexity of the LHC environment, so first of all, the fact that you have the same data sets constraining both, and also that you have kind of effects that mix new high energy with low energy, might intertwine them. And this is what, with my ERC collaboration, we are trying to answer. So is there an interplay between the SMEFT fits and the PDF fits, even because this is something I want to make you notice. So if you look, for example, the NMPDF 4.0, this is an anti-up distribution at 100 GeV. So this is the fit without the LHC data. As soon as you add the LHC data, you see that they have a strong constraint on the large X, but also they shift the PDF beyond the error bands, okay? So it's not that it's compatible inside the error bands of the reduced data set, it's shifted upwards, okay? So there are some incompatibilities, but we don't know what is the origin. Could be experimental, could be theoretical, could be due to new physics, okay? So I think these are the kind of questions that are relevant for if you want to do precision phenomenology. Okay, so what are the questions? From the point of view of the PDFs, the question is, how do we make sure that being greedy and keep adding high energy data, we are not fitting away inadvertently some of the new physics effects that are in the tails? And from the point of view of this SMEFT, what PDFs do I use? Should I make sure that I'm using a clean set of PDFs for the SMEFT analysis? How to define it? Do you want to use a set that doesn't have any high energy data, and so on? And how would the bounds change if I was consistently using PDFs that include in the fit the same effects that you put in the SMEFT fit? So in particular, the last question, this is something that if one had some technology to do simultaneous fit, this could shed light into the interplay, into the correlation between the coefficients that you have in the SMEFT expansion and the coefficient that you have in the PDF parameterization. So this is what I'm going to talk about in the first part of the talk, and then I'm going to talk about the first question at the end, okay? Good. So the first study that we did was 4 years ago with Céline Degrand and other collaborators, and it was a very kind of simple scenario based on a kind of very simple and limited methodology. So the idea was the following. So because all our PDF fits are based on a lot on DIS data, so let's see what happens with DIS data. So if there are some 4 fermion operators that are relevant already at the few hundred GeV that are probed by the HERA data, okay? So the idea was we took only right-handed 4 fermion operators, so just 4 operators, which were, lepton flavor blind, but we split the quark flavors to evade the LEP constraints. And we took, somehow a region in the Wilson coefficient space that was still allowed by LEP. And we tried to see, okay, let's inject these coefficients and make fits of the PDF by setting these coefficients, instead of setting them to 0, to the values that are allowed by the current bounds. And it was interesting because what we saw was reassuring, because we saw, for example, that, let's say this is one of the maximum deviations that you can have, that you are allowed by the data. and the gluon changes a bit. Okay, so this is the maximum change in the scan that we did. But it was nice to see that if you were using, the fit that you were having here had a worse chi-square, so a worse data theory agreement that was deteriorating as you were adding more high energy data. So this was a sign that, in a sense, at least in the scenario that we consider, the DIS data are quite safe, because a non-zero Wilson coefficient would introduce some deviation, but this would be spotted in a PDF fit, because you would notice that the agreement deteriorates and scales with the energy, which is the effect that we see from operators that grow with the energy, okay? So this is good, it's a good news in a sense, because we don't want anything that messes up with the DIS data, okay? And then with Admir, and we said, what if we look instead at the Drellian data, because they reach a much higher invariant mass. So at that point, especially, there are lots of projection of data in the high Lumi LHC that have been considered in the study of these oblique parameters, like STU, WY, but WY are the ones that grow with energy, okay? So there were some studies like this one that showed the potentiality of this data in constraining the W and Y operators. So these are basically these universal four-factor that encapsulate the effect of new physics, universal new physics, like a new Z prime or a new W prime that mixes up with the standard model. They are basically linear combination of four fermion operators, and the effect grow with the energy. So the W and the Y are the ones that really affect the high energy tails of the Drellian invariant mass, okay? So we said, let's just redo this study, okay, but now including the effect of the PDF. So let's see what happens. So what we did again was a limited thing, was just a scan of benchmark points in the W and Y space. And we tried first with the high mass neutral current Drellian data that we currently have in PDF fits. And these are the two parabolas that you find. So basically, okay, this is the one-dimensional scan, but we have also the two-dimensional. So the one here, so the blue line is the normal thing that you have with the standard model PDFs, okay? And you scan over the values of the parameter, and you see you have, delta chi-square equal 1 gives you the bound. The orange line is the one done with this methodology. So that basically the PDFs in each point are calculated with that value of W in the theoretical prediction. So it's not done with C equals 0, but with C with the coefficient equal to this value over here. And you can see that the parabola gets broader, as one expects, but the effect on the change in the bounds is not dramatic. In a sense, it's a small effect, okay? But again, it was interesting to see. But then we said, okay, what if we do the high Lumi LHC projection instead of the current data? So what if we go to higher energy? Yes. No, in a sense, yeah, that's the point. So when you go into dimension, you do a space, so you have a fluctuation of the chi-square. So you have to do a lot of points and a lot of, in our case, replicas in order to get, but then you get good parabolas. In the paper, we have all the error bands, and you see that the parabola is a good fit. Yes. Yeah, that's why. That's what I'm gonna say. Exactly. So that this method, which is the same one used by Jun Gao, so there is also another paper by the CT collaboration that does this kind of scan, is interesting to understand, but is not generalizable to many Wilson coefficients, because you have to do a huge scan, and for each point you have to do a PDF fit. So it's very expensive, okay? Okay, but anyway, we did it with the high Lumi Drellian, and what we found was very interesting, because if you go to much larger value of the masses, which is what you can reach in the high Lumi, you see that actually, this is the SMEFT PDF. So this is the kind of contour of the parabola, and the bounds do get much larger, okay? So if you look at the standard model PDF or the SMEFT PDF, so the one in which I change, the contour dramatically change, okay, by a factor of 2. Again, these results, I wouldn't bet my life on them. So on the size of the enlargement, in fact, then I tell you that if you use a better methodology, but still, you can see that something is happening. And the other thing, which is the one that triggered the study that I'm going to present in the end, was that contrary to what we saw in DIS, so this is the chi-square as you include higher and higher invariant mass data, okay? So clearly, if you use standard model PDFs, but new physics, you get a worse chi-square that increases as you raise the cut of the data that you include. But if you use W equals 0 standard model PDF, or W equal to whatever value you can reach in the scan, but with the SMEFT PDF, you have exactly the same chi-square, even increasing the cut in the invariant mass. So this means that contrary to DIS, there is an effect of compensation between the new physics that you inject and the PDFs. And that's something that I will quantify later on. Okay, but as I said, the scan in the SMEFT space is limited to a few Wilson coefficients. And also, as Maria Vittoria was asking, there are lots of uncertainties in this scan because you have to do lots of statistics. Okay. So what my student, Cheyenne, came up with was this idea that actually turned out to be good, really feasible. So you take a PDF fit based on NMPDF 4.0. So this is the NMPDF neural network that you give an X and gives you out the independent parameterization of the quark, anti-quarks, and gluons. But then you add, you make the dependence of the observable on some physics parameter C explicit, and you add an extra layer to the neural network. So this gives you an extra layer, and the loss function keeps into account the correction from the parameters that you get into the extra layer. And then basically you perform the minimization of the chi-square or the loss function over the joint space of parameters. So the parameters of the neural network and the parameter here. What is interesting is that this can be done not only for SMEFT parameters, but in principle, it could be done for PDF in alpha S, mass of the top. And so we haven't tried it. So we are trying it, but okay, I tell you just about the application on the SMEFT. So exactly. So for the SMEFT, it's simple because you have your standard model observables and then you correct them with a linear or a quadratic factor, depending if you take dimension 6 or dimension 6 squared operators, okay? So basically, you separate the parameters that go on the PDF in the standard model prediction, and then you have times the thing that depends on the SMEFT. And it's nice because you can also add the quadratic terms, now because these are non-trainable edges, because they depend on these lines, they're not independent, but you can add it together, not to modify the observable. So we tried, and in this paper, we tried to do it exactly in the W and Y. And each of these points is the best fit PDF, also the best fit for these Wilson coefficients, okay? And then you do a replica sample in the joint PDF and SMEFT case. So this is much easier to do. So statistically, we do 1,000 replicas in this joint space, and this gives this contour green that you see. So basically, you can compare the fixed PDF fit to the high Lumi LHC data to the simultaneous fit of the same data in a global fit. So it's not just the data, you put them in a global fit and you let the Wilson coefficient vary. So the broadening that we observed before, it's similar. So we saw a factor of 2 broadening of the bounds of the W and the more moderate factor for the bounds of the Y, okay? So this is interesting for the SMEFT coefficients. And for the PDF also is interesting because, you know, these in green are just the standard model PDFs that have including the high Lumi LHC data for the high mass Drellian. And in orange, you have the high, you know, this PDF, which have been fitted together with the W and Y. So you can see that they're compatible, but they have a larger uncertainty in, so this is the luminosity for QQ bar. So it means that the PDF in the large X region have a larger uncertainty that keeps into account the fact that the data that are included might have some effects that comes from new physics, okay? So this is a nice result, yes? No, they are left alone. There's yes. Yeah, PDF parameters, exactly. Exactly. When you take a high energy data, you add it into the fit by just seeing the effect on the PDF fit by themselves without considering the possible variation of the Wilson coefficient, and when you feed them simultaneously with these two parameters, okay? Yeah. As we normally do in the NMPDF fits, it would be an extra thing to do the other parameters. It can be done in principle, but it's not trivial, yeah. Okay. But it can be, in a sense, this methodology is a way of doing it, which is less cumbersome than other ways in the NMPDF. Okay, cool. So we said, okay, good. These are only two things. Let's see if we had more, if it still works, you know, because in principle, there shouldn't be any limit in the number of Wilson coefficients. So after testing the methodology on a small number of Wilson coefficients, we wanted to stress test on a large SMEFT parameter space. So what we took, it was all the run to top quark data from Atlas SCMS. And basically, that involve four basic processes like inclusive TT bar and asymmetries, single top, inclusive and differential, associated T bar and vector boson production, and associated single top production. So the ones on top here are the most important for the PDFs, and the one below here are more important for the SMEFT. Okay, so the idea is that we have 25 or 21, depending if you're linear or quadratic, dimension 6 operators that you add on top of the PDF parameters. So in this study here, we did three things. So first, let's say we add all this data, which are 78 new data points in the top sector just to the NMPDF fit. So you take NMPDF 4.0, you add this new data, and we see what happens to the PDF. Here, everything looks consistent. So like in blue, you have the NMPDF 4.0 data, you add more data, the gluon has a smaller uncertainties, and it's compatible with the one before. But notice that if you look at the gluon in which there are no top data, and you add all this top data on top of the one that you have in the NMPDF 4.0, the two error bands of the gluon go more far apart from each other, okay? And the same you see in the luminosity at large invariant mass. So it's always a problem in the high invariant mass. Okay, then we do a SMEFT only fit. Okay, that's maybe a bit less important, but it's still. So the new data set as compared to the old data set, for example, the one included in the SMEFT collaboration, and you can see that adding data increases a bit the constraints, and this is more evident at the quadratic level. So if you compare the bands for the green and the bands for the orange, okay. So in a sense, and all of this was benchmarked against global SMEFT fits, okay. So that was interesting because it means that our thing works. But then we said, okay, let's look at the correlation between the SMEFT Wilson coefficients and the PDF. So we saw, so these are the correlation coefficient between each of the 25 Wilson coefficients and given PDF flavors. And what you notice is that the biggest correlations are highlighted here, are between the gluon in this region, so 10 to the minus 2, 10 to the minus 1, and the singlet, which is the sum of quark and anti-quark, which is correlated to the gluon. So we expect the biggest change in the gluon when you do a simultaneous fit by looking at these correlation plots. And indeed, this is what happens. So the simultaneous fit is the green thing. So this is the gluon luminosity. So so the blue is just the PDF fit. The green is the one that you do simultaneously with the 25 Wilson coefficients. and the orange is the fit without any top data. So what you see is that the simultaneous PDF fits nicely sits between PDF only fit without the top and the one in which you include the top with larger uncertainty in the large invariant mass region. Okay, so we see, again, these are small effects because everything is done with current data, but it's already significant effect. So if you want, this inconsistency between these two lines is cured by the fact that you keep into account effects that are still allowed by the data, okay? Instead, the Wilson coefficient basically are totally stable upon the PDF variation. So if you do just SMEFT fits with the full top data sets, and you use fixed PDF, so without any top data, and you do the simultaneous, you get similar bounds, okay? And that's in a point of stability, which we didn't see in the Dralian. But anyway, so I think so the answer is, it really depends on the sector. So in the case of the top, the PDF are shifted, the Wilson coefficients remain the same. And in the case of the Dralian, the PDFs are compatible and the Wilson coefficient broaden. Okay, again, one is high Lumi, one is current data, so one has to be careful in this comparison. But I think we did find some quantitative results about the interplay. Okay, any questions about that? Not, I keep going. Yes. Fixed, yes, 170, I don't remember, 3.1, I think is the standard, yes. This could be something that one can do with the Simunet things. Yeah, we are trying with Alpha S and MTOP now. Yeah, we'll see. I'll let you know. Okay, so then that's the last thing I wanted to mention. Sorry, I'm a bit late, but okay. So this is all about simultaneous fit. And now we say, okay, can we try to answer, having seen all this sign more precisely to this question? So can PDFs absorb new physics? So the idea is to exploit the closure test. So in an MPDF, we routinely test the methodology via some closure test in the data region and some future tests, okay? But the closure test assesses the methodology robustness. So the idea is that you input a true PDF. So instead of having the real data, you generate artificial data with the true law of PDF, like that it comes out down from the sky, you know, I don't know, MMHT are the true PDF, fine. So you generate all your data with the truth that nature is giving you. And then you check if doing your fit, you find the truth, no? And if the uncertainty is faithful. So our idea was, okay, now imagine that on top of the true PDF, you can inject in the data also the true UV model that nature is giving you, okay? So then you generate artificial data, assuming the true law of nature. So true PDFs plus the true new physics. And then, but you fit the PDFs blindly, assuming the standard model, as everybody does, okay? And then you say, can PDF absorb the signs of new physics? So we try to answer quantitatively in this closure test method. So this is the paper if you want more details. Again, this can be done with any model you like, but the time and resources were limited. So we tried with the Z prime and the W prime model because for us it was easy because they were already parameterized by the Wilson coefficient that we studied before. So we took W and Y, we already had all the theoretical predictions and blah, blah, blah. So the result is that basically, and everything is in the high Lumi. So with Z prime, cannot be absorbed. So that's interesting. And instead, the W prime can be absorbed. So what do I mean? And why is this difference between these two models? Okay, so okay, so first of all, we checked that if we take this the UV model, we stayed in a region up to 3.5 TeV in the high Lumi that can be described by the SMEFT, okay, but that's just a technical thing. And then a region in which the tails are affected by new physics, but we wouldn't see it because the PDF uncertainty is huge in this region, okay? So we would need to add this data to constrain the PDFs, okay? So that's the point. So then there is this magic number, so W equal to 8, 10 to the minus 5, which corresponds to a W prime with mass of 14 TeV. So what is interesting is that we inject this new physics in the data, and you see that W is the orange histogram of the chi-square, because we have to do lots of data variation. But the point here, the message is that the chi-square is perfectly fine as the standard model. So you wouldn't notice that these data have incompatibility with the bulk of the other data sets that you have in your PDF fit. So you can fit them perfectly because the chi-square distribution is exactly as it would be in the standard model fit, as if you didn't have the, but the PDF changed a lot. So you have to compare, probably I should have matched the color. So this is the QQ bar luminosity, so the one that goes into the neutral current, UU bar plus DD bar. And this is the standard model one. So you see that there is a big shift that goes completely unnoticed. So you find PDFs that are different from the ones you would find if there was a new physics that are still perfectly compatible with the data, okay? So in this case, we are saying, yes, so for this particular value of W, for this particular new physics model, if you want the quark PDFs, in particular, we check the anti-quark PDFs at large X manages to compensate the effect of new physics and to fit it away, okay, in a way that would be visible. So this was something that happens only with the W prime. Why? Because the W prime manages to change the neutral current data in the fit and the charge current in a way that are opposite, and they manage to get away from each other. Instead, the Z prime would only affect the neutral current data because of the kind of interaction. So that wouldn't go unnoticed. So if you do the same histogram for Y, you would notice that if you had the Z prime with a mass of the same order of magnitude, this would be spotted at the level of incompatibility. So anyway, I can show more. But what would be the consequences of this contamination? So first of all, that if you do a SMEFT fit of the W coefficient, you would find this value and you would miss the real new physics range, no? Because you wouldn't see the new physics where it is in a SMEFT fits. The second consequence is that because you are using this contaminated PDF, so that they are different from the standard model simply because they absorb new physics, you would see new physics even where there is not. So for example, again, this is all in the high Lumia. So this is W per production. You would see a deviation that is not real. It's only because your anti-quark have this shift, which comes from having fitted away new physics. So you would say, oh, wow, there is a tension with the standard model, but actually we know that the W prime model would not cause any effect on the W plus W manu per production. So the point, I think now, is how do we avoid this contamination? So we tried in the paper to devise some PDF independent observable ratios. In this case, for example, you would see that independently of the PDFs, either in the W plus W minus or in the neutral current Rayleigh, there is some deviation, okay? But you wouldn't know which one, if it's the numerator or the denominator. And also, everything is some soft indicator that there is something wrong, but nothing is conclusive. So we do have a long section about that because we did try everything. We said, okay, what if we had the LHCb data that are at large rapidity? They wouldn't constrain the anti-quark. So basically, the message is that in the NMPDF fit, we don't have strong low energy constraints on the anti-quarks at large X. And this is what allows this to get away with this kind of new physics contamination. So the message, I think, of this paper is that we need to have more accurate low energy, large X constraining measurements to really disentangle the effect. And this is a strong motivation, for example, for the study that you did, like to look at the sequence data or at the projection for the EIC data or the phasor new data. So all these kind of data that are at low energy, so they don't have contamination from high energy growing effects. but that constrain more strongly what is not constrained yet. So I think it's nice because the message is that there is a nice interplay between the low energy and the high energy words. Okay, so I think that's it. So I already said everything I wanted to say. I leave it on to the conclusion. So if you have questions, you can ask me. Thank you very much.
Thank you very much for this nice presentation. Questions, I see.
Thank you for the new physics stuff. So I think what I would find interesting is the following. Assume you have a signature which points to a discovery. Yeah. So inject something, pretend that here, fantastic, we find a new resonance somewhere, which has whichever quantum numbers. And then with a standard model assumption in the PDFs, right? And then include this novelly discovered, whatever it is, in the PDF fit and see whether you still see it or not. I mean, I think this is the question one should really ask, right? So
that's the question that we did try to, it's a question that we exactly asked. The only thing is that here we just took, like, if you want a naive Z prime or W prime model, but we already have some script that release this, but now we're gonna have a public tool with all this simultaneous fit and also this possible contamination, so people, you know, can do what you suggest to play with a more realistic model injected in the data, exactly as we did here, and see if the global fit of PDF have some signs of tension with the model that you put in by fitting it in the standard model. Is that what you were asking?
Yeah, more or less. I mean, so maybe I didn't get it completely. You assume you have a discovery, or you just say I have a heavy particle which might contribute to the PDFs, but we will not have a discovery. So my assumption would be really you have a clear, like a 5 sigma effect using whichever methods for new physics. And then the question is, can this, you know, does it get higher or lower? I mean, if I include it in the, if I have 5 sigma, then I would say, let's assume it's real. And then you have to include it in the PDF. So maybe it's a similar question you can ask. I didn't follow this, yeah, but before and after Higgs discovery, for example, I guess before the Higgs discovery, there was no Higgs at that mass in the PDFs, and then you insert the Higgs at a certain mass and see how it changes. And what probably was not done is afterwards seeing whether the discovery would still have been a discovery or not. But this is what I'm asking,
I see what you, but the point is that it's not, it's more subtle because you know, the new physics does not affect the PDF. It affects the data that you routinely put in a PDF feed.
Yeah, okay.
So for example, the Higgs data, we never put them into a fit, you know, so all the Higgs data are excluded from the kinematic plane I showed you, and in the kind of observables, the Higgs doesn't have any effect. So the Higgs is an example such that we wouldn't see it in our fits, no? So whether the Higgs is there or not, if you want, the parameters that go in our Lagrange are unaffected. But if there is some more motivated model that, for example, affects the top or the jets, we haven't looked at the jets yet, and these could be absorbed in the gluon, that would be very interesting, you know, if anybody could play with that. So our idea is to give a naive example and then let BSM people play with it if they want to. We don't.
I mean, maybe because you say would not see in, sorry, I'm looking at your slides here. Maybe we should do it for everyone. I don't know, but because I see the statement, we would not see indirect effect. But the question is really assuming effect. How would you see it if you include somehow?
Yeah, that's, I understand. Okay. Yeah.
But thanks. Other questions, comments?
Things that you do not use for the PDF fits will start having an effect, because you did the example of the Higgs, but a lot of Higgs observable are used in SMEFT fits, and the operators talk to each other, right? So they will start having an effect on PDF fits as well.
Exactly. No, that's a very good question. I forgot to mention that in this thing. So for example, so the tool that we are going to release here will have the possibility of including in a fit also PDF independent observables. So you can also in the public release that is in a couple of months, hopefully. So you can have electro-with precision observable that are independent of PDF. But if you put it in a simultaneous fit, you need to have both, no? Because if you do a global fit beyond the top, so for example, even in the top, for example, the elicities of the top, we don't use the PDF, or even for associated single top, they have such a little dependence on the PDF that we just treat them as PDF independent observables. And in the new fit that we're going to release, we will have Higgs observable, electro-with precision observables. So you can do a normal global fit or a normal global fit where the data that depend on PDF have the opportunity to also let the PDF vary. Yes, thanks for the question.
Okay, so we start in the Sultan.
Thank you. Do you know, or are you aware of similar studies with other PDFs? And if so, do they get similar conclusions?
Yes, so here there are two global SMEFT collaboration that looked, no, even more, I think, but we only check with two because my collaborators, one was involved in FitMaker and one was involved with SMEFT. So it was nice to have internal people because we could check that, the bounds that we obtained for the Wilson coefficients with our methodology were totally compatible with the bounds that they had. So it's good because we are in touch with them because there are lots of details, just leave alone the PDFs, but in the SMEFT parts that, we found were incorrect thanks to the benchmarking. So, yeah.
And different kind of question is, you do a simultaneous fit of PDF and SMEFT coefficients, let's say assuming 25 SMEFT coefficients like you did in the top sector. And how robust is your conclusion against including more SMEFT coefficients? Because let's say you see some effect of new physics, but what happens if you include 500 coefficients? Will you still see the same?
I don't know.
Or maybe the effect you see is simply the result of some other coefficients that you think are not really important, but eventually they turn out to be important.
Yeah. So I think this new thing that we're going to release shortly will have more. So I think 38, if I'm not mistaken, including some of the Higgs and the electroweak. So we'll see what happens there. But I think what you're saying points to so something which is not clear to me yet. We have to understand better, how these two things relate with each other. So the injection of a new physics signal into data to check, or the result of a simultaneous fit, or what do you do with these MEFT PDFs that you get? So this is something that we are thinking about, but we are not sure about the answer yet. Yeah. All marginalized, it's all coefficients together, yeah.
Allora, two questions. First is standard model effective field theory fit. You do a NLO, right?
Yes.
The PDF that you are considering are NNLO or NLO PDF in all these pieces?
NNLO.
Okay. So you're in any case working with NNLO PDF and not with NLO PDF in all these.
Yeah, because it's two different expansion. You have the 1/lambda squared in the. First of all, there are no SMEFT predictions at NNLO.
In fact, that's my point.
But
then one doesn't work with NLO everywhere.
You use the best you can use in both words, even because the SMEFT is suppressed by the 1/lambda squared. So in a sense, if you want the QCD effects are suppressed by these things as well. but they're important because they mix operators. So that's why we include them.
I see. And the other question was on the top fit.
Mhm.
At some point you showed some plot with the top at large X. I mean, the PDF fit with and without the top. At large X, even without a standard model effective field theory.
These.
No, maybe later. No, after. I think it was, you showed two PDF fits that don't agree at all. I mean, with the top data, without top data.
No, I think the top data is this. So in a sense, if you look at the orange and the green,
They
they
agree.
don't agree. In a sense, there is the blue in the middle, so it's a bit difficult to see. But yes, they don't agree within 1 sigma. It's not a
And my
huge.
question is, okay, but this is not there is no effect beyond the standard model in this disagreement, right? I mean, this is done all, forgetting about BSM.
Yes, exactly.
Ecco, I guess you investigate why they don't agree. Which process, which data are responsible for this difference?
But it's that's a usual thing in a sense. There is so everything is within our criteria of compatibility. Okay, so each PDF collaboration chooses a criterion for compatibility. So there is a tension between the JETS data and the top data.
The JETS.
Okay. Yes,
that's the problem. The big question mark.
Yes.
Okay.
That pull in different directions. The large X blue one. Yeah.
Mm-hmm. Okay. Thanks.
Question that I had is how much of the conclusion that you get depends on the fact that the SBSM you decided to use the SMEFT parameterization. So just a simple example, typically you see large effect in SMEFT at high energies, right? So you have also there you see all the bands that have a difference when you go to high invariant mass.
Yes.
But imagine that you have some physics that is hiding at lower energy.
Yeah, that's a very good question. We haven't, in a sense, so this thing of, so in principle, for example, the contamination, so the thing that of generating data, you can do it with any model. You don't need the SMEFT, no? So for us, it was just a technicality because we had all the predictions ready, but you could inject any new physics you like. And then the only thing you have to do is you have to compute the the kind of artificial data, so the theoretical prediction you get for all the observables you put in a PDF fits that come from your model. And then you see, can I do a global fit of this thing? Would I spot new physics? Would I see an incompatibility or not? So actually, that's something that we thought about. We don't have an answer yet. So if you have an idea of some other model, this is what we encourage people to do. In a sense, this is very generic. You can try other models. You can try.
Imagine even just sometimes even if I think even SMEFT could give you at higher order effects. For example, imagine like at the threshold of TT bar, if you have another scar that is exchanged, you have this Sommerfeld enhancement effects. That these are at the threshold, are not in the tail.
So that would be, if you have a concrete idea, would be happy to give you the, to work on it, because in principle, you can do anything you want. So we were looking at detail because we were lazy. We had things about details.
No, but obviously,
we don't have.
I think a good idea starting with the SMEFT.
Yeah.
So I'm not going, I'm just wondering how much of the conclusion are the same.
And that would be a good question.
If you just change, the region of X where the new physics is dominating.
Yeah, that would be a very good question. My suspicion is that it would be harder to absorb it because there are more constraints from the data. But you never know. These are subtle effects. We were not expecting to see what we saw, if you want. So. No, that would be another thing to do. So also the global SMEFT fit at the moment do not include the RG running of the Wilson coefficients because they mix all the operators. exactly, it becomes more complicated. One should do it, but yeah.
Okay, so I see we had a lively discussion, lots of questions. Maria is still here for the rest of the week to address all other questions that come up. And for now, let's thank her again.
Thank you.